Previously, we were talking about wired communications, typically using, for instance, twisted pair cables and fiber cables. Now we will talk about wireless communication. Then we will talk about typically physical basics related with the communication wireless, that is without the use of any type of cable, and we'll will focus our attention on the standard 802.11 from the IEEE that establish standard for wireless LAN communications. Then, well, the basic principle of wireless transmission, data exchange is based on the transmission of electromagnetic waves across the air or the vacuum. A wave type converter called antenna converts the conducted wave into a free space wave transmit side and back again receive side. An antenna is used in order to transmit the wave, the electromagnetic wave, and another antenna is used to receive that electromagnetic wave. For transmission, the user information is modulated to a carrier frequency. This is different compared with the baseband mode transmission that we typically use when we use guided medias like the copper cables and the fiber cables. Different carrier frequencies have different propagation characteristics. This is important to be taken into account because there are typically pros and cons associated with the frequency that we use as a carrier. Here we are different frequencies from the lower frequencies to the higher frequencies. We already talk about a little about that kind of frequencies, typically associated with light, typically in the order of hundreds of terabits, terahertz. But in this chapter, we will focus our attention on typically this scale, this spectrum of waves, typically the order of gigahertz. It's what we call microwave signals. Then here you are different frequency bands used in different technologies. For instance, in the mobile phone technologies, GSM, LTE, but we focus our attention on those frequency bands, typically used in the wireless LAN technologies that were specified by the standards called 802.11. But those frequency bands are used by other technologies, for instance, by Bluetooth or WiMAX. Here you are another description of the use of the frequency bands, in this case, in Germany. Remember that almost every spectrum frequency is controlled by the countries, by the state, and typically those are the bands, the frequency bands that are licensed by the Germany state. But when we use typically the band of, for instance, 2.4 and 5.5 gigahertz, will see that those are unlicensed frequencies that don't require the authorization of the state to be used. Then those are what we call the ISM band, the industrial and scientific medical application spectrum that could be used by that kind of applications and are unlicensed. That is, those bands are reserved for islands and licensed use. Then typically there are some bands that could be used without a license. This is one band of 900 megahertz. The other on the band of 2.4 gigahertz. And finally, the band of 575 gigahertz. This is the bandwidth in each of those bands. Typically, the unlicensed use, unlicensed use of those bands is possible when the transmission are of low power. Typically, for instance, lower than 1 watt of power transmission. This is another physical basic that we need to understand in order to, for instance, pay attention particularly to some characteristics. Typically, this is for instance, the transmission antenna, and we place anywhere here the receiving antenna. Then, if the receiving antenna is farther, then the power of the transmission signal will be typically lower in the receiving antenna, and then what we need to understand is that there is a relation where the power decrease with the square of the distance, and then this is characteristic very important to be taken into account. The other characteristic that is very important to understand is that the attenuation, what we call the free space path loss, that is the attenuation, is increase with the square of frequency. That is, if the frequency is higher, the attenuation is higher. Then, for instance, what we will see is that using 2.4 gigahertz, we could reach um, some antennas that are far away than the antennas that could be reached using, for instance, 5.7 gigahertz. And then remember the relationship between the frequency and the distance in order to understand the behavior of the power attenuation in the free space path loss. Then typically, in order to understand that relationship, you have to remember those equations. The free path space path loss is equal to the power received divided by the power transmitted. It is a fraction expressed in that way. And that attenuation is equal to this equation. For P per distance per frequency divided by the light speed, the light rate. Then, if we apply here the calculation based in the use of decibels as units of power, we could transform this equation in this other equation, and remember that this equation you need to respect the units. That is this member could be different if we use here the distance. We use the distance in meters or in kilometers, or the frequency in hertz or in megahertz or in gigahertz. But the literature shows the different equations that we could use of in the calculation of the free space path loss when we specify the distance and the frequency in different units. What is very important to understand is that the free space path loss must be included in what we call the power link budget of a radio communication system. And the power link budget, in fact, is an equation where we specify the transmission power, the antenna, the distance between antenna, the antenna of in the receiver side, and typically, for instance, the signal noise ratio supported by the receiver device. And with all that equation, we could the goal of that calculation with the power link budget is to ensure that sufficient radio power reaches the receiver such that the transmitted signal is received intelligibly. When we say intelligibly, we mean with signal to noise ratio higher than the minimal signal to noise ratio supported by the receiver, in order to, for instance, decode the information. Here you are, the same equations, the same formulas that we already showed here. And in this case, for instance, this number is the number that we need to use when the frequency is specified in megahertz and the distance is specified in kilometers. Well, then the categories of radio transmission methods, we could see here the different names that we use to identify the technologies depending on the distance the cover or the areas covered. Then typically in the very narrow distances, typically in the areas of the personal reachability. Here we are, for instance, the Bluetooth technology. We talk about wireless personal area networks, that is WPAN. In the order of 100 meters to 1,000 meters, typically we talk about wireless local area networks, WLAN. And this is the object of our study in this chapter. Typically, the technologies specified by the standards 802.11. And there are other names, for instance, typically WNAN from Neighborhood Area Network, or WMAN for Metropolitan Area Networks. And finally, W1, that is wireless wide area networks. And typically in this case, we have different technologies related with cellular phone networks or cellular networks, and some networks are used for what we call IoT, Internet of Things. In order simply to remember the different standards, 802, remember 802 comes from February of 1980. In February of 1980, the 802 or 82 working group of the IEEE, of the Institute of Electrical and Electronic Engineers, where in that date, this working group was were created, and this working group is then the group that work and define the different all those different standards. Typically, we use 802.3 when we use Ethernet with CSMA CD as the medium access control. The 802.2 that specify the sublayer called logical link control, and or for instance, typically we will study now 802.11, that is the standard that specify the different technologies for wireless LAN. Or for instance, This is 802.15 that is used for Bluetooth, or 802.16 that is used for what we call the WiMAX technology, used in the typically in the wireless NAN or wireless MAN, neighborhood or metropolitan area network. In this chart, we could see the different technologies, the different wireless network technologies, and we could compare those technologies based on the bandwidth, and the distance and the cost. Then is a three-dimension chart. In this axis, we have the different data rates or bandwidths supported by each technology. In this axis, we have the distance, and with those colors, we have the cost of each technology. Then typically, cellular technologies are very interesting, but are present a very high cost. The other technologies are cheaper, but for instance, in the case of Wi-Fi, we could cover more short distances, typically tens or hundreds of meters, but no more than that. Or, for instance, in the case of Bluetooth, we could transmit at within what we call a local area network, like in the case of Wi-Fi, but at lower rates. In this slide, you could see that there are a lot of standards related with wireless LAN, that is with 802.11. For instance, the first one was 802.11 with rates of 1 or 2 megabits per second, using the 2.4 gigahertz band, and using the transmission method called FHSS and ESSS, both using a particular methodology of multiplexing that is called spread spectrum, using code in order to separate the channels. The 11B standard that could reach 11 megabits per second, using a slightly different methodology of transmission called HRTSS. 11A and 11G that reach 54 megabits per second in different bands, typically A in the band of 5 gigahertz and G in the band of 2.4 gigahertz, using different transmission method called OFDM and 64 QAM. Those are the combination of modulations. and 11N that could reach 600 megabits using several channels of 40 megahertz of bandwidth, and different particular they use the same modulation used in the 11A and 11G, but for instance, using a new methodology of transmission called MIMO, that comes from multiple input, multiple output, and it is related with the use of several antennas to transmit and receive. Finally, we have 11AC that could reach 1 gigabits per second and use channels, more wide channels than those used in 11N. And finally, 11AD that reach 7 gigabit per second, using, for instance, any of those bands. The difference in the bandwidth that each of those technologies could reach is related with the use of particular modulation techniques that are typically associated with what we already see in the previous chapter, and that is the use of the Fourier composition of the signals, and we could see a technique that permit to generate different signals with different frequencies and phases, and those different signals that are orthogonal, that is, that are independent, could be used to transmit, for instance, different bit streams in parallel. Then the parallelization permits to multiply the bit rate or throughput that we could reach using those modulation techniques. Then typically, we already see that some particular modulation techniques are used in each of those techniques, simply in order to, if you would like to study deeper, you need to search, to look for bibliography that that explain deeper those techniques. But typically, for instance, the FHSS is comes from frequency hopping spread spectrum, and in this modulation or multiplexing technique, there are typically different channels, and in fact the transmitter change frequently the frequency of transmission, perhaps, for instance, more than two or three times per second, and hopping from one channel to the other, choosing any of the 78 channels that are available in the in the frequency range used by this technology. Typically, in 2.4 gigahertz band, frequency band. In the case of DSS, DSS, remember, is used in, for instance, in 11B, that is 802.11b, and in fact, we could split the frequency band in several channels, and we use typically modulation within. We modulate the signal, the carrier, using the information signal, but with with a code that is generated in a way that that permits the separation the separation of the digital signals in order to reduce the the influence or the superposition of the signal. The signals are superposed typically, but using a code with technical code called spread spectrum, the receiver could separate we using that code could separate clearly one digital signal from the other. Finally, in the case of 11G or 11N, we could use other multiplexing technique called orthogonal frequency division multiplexing. In this case, we could transmit several signals in parallel, symbols in parallel on typically 52 different frequencies, and this is multiplexing methodology or technique that is used in all those standards, that is 11A, 11G, 11N, and others. In one of the technologies, we start to use typically technology called MIMO, multiple input, multiple output. Then here we will see some description about this technology, MIMO. But before to talk about MIMO, we need to talk about fading. Fading is the attenuation of the transmitted signal power due to various variables during wireless propagation. The variables could be the line of sight. For instance, there is a wave that propagate following the line of sight between the two antennas. Another could be another path of the wave could be different because there is a barrier and there is a diffraction phenomena that modify the propagation, the direction of the signal of the wave. Or, for instance, a reflection path, that is a signal that is reflected and then is received at the receiving antenna. And if this occurs, then there are typically different wave paths. Each one we will introduce different delay and perhaps a difference in the phase of the wave. Then we say that fading occurs when there are significant variation in received signal amplitude and phase over time or space. Fading can be frequency selective, that is different frequency components of a single transmitted signal can undergo different amounts of fading. And then in order to take into account this behavior of the wave propagation, we could use this technology, this mechanism called MIMO, multiple input, multiple output, is an antenna technology for wireless communications in which multiple antennas are used at both the source and the destination. The antennas at each end of the communication circuit are combined to minimize errors, optimize data speed, and improve the capacity of the radio transmissions by enabling data to travel over many signal paths at the same time. Creating multiple versions of the same signal provides more opportunities for the data to reach the receiving antenna without being affected by fading, which increases the signal to noise ratio and reduces the error rate. Then take into account that some technologies use MIMO, and thanks to that, they could enhance in fact, the bandwidth and reduce, for instance, typically the error rate of the transmission. Well, remember that layers, the 802.11 is in fact a specification of the two lower layers, the physical layer and the data link layer. We already talked about the physical layer tied to those technology wireless LAN specifications. But over the physical layer, we need to implement the data link layer, and there we divide this layer in two sublayers, the MAC sublayer and the logical link control sublayer. I hope that you remember this. We already see this in the Ethernet chapter. But in fact, the logical link control is the same used in the if we transmit typically frame Ethernet frames, for instance, across a local area network. But in the particular case of the wireless LAN technologies, we use some different MAC sublayer protocol. We use a different MAC frame format. We will see those particularities, and we use a different methodology or algorithm to access the shared media. And then we use a shared media, typically the wireless channels, and we need to arbitrate, we need to control the access to that shared media. That's why we need to implement different medium access control mechanism or protocol. Then we'll talk about first about the frame format used at the MAC sublayer of the wireless LAN technologies, and after that we will talk about the algorithm or mechanism used to control the access to the shared media in wireless LAN. Then the frame structure, that is the MAC frame of the wireless LAN technologies, is this one. Is a frame slightly different compared with, for instance, the Ethernet frame. Here we are. One of the differences is that there are several fields of control and management, several fields of addressing, not only two, not only source and destination, but there are until 4 addresses that could be used. There is, for instance, the possibility to sequence the frames, and for instance, there is a field called duration. We will see that when we talk about nav. Then typically now we will talk about well, the type. The type is not equivalent to the frame type of Ethernet. It's another type. The specification of typically the protocol that is encapsulated within the frame is not specified here, is specified in the LLC header, in the logical link control header. Then here the type is because in the case, for instance, of Ethernet, there is only one frame type, that is what we call an unnumbered information frame. But in the case of the wireless LAN MAC frames, we have several types, different types of frames, and even several different subtypes associated with each type. We use, for instance, those flags in order to indicate if we transmit from a distributed system, that is from an access point, or we are transmitting to a distributed system, that is to an access point. And this is something that we will see when we study deeper the addressing methodology used in the wireless LANs. Well, there is, for instance, more fragment, retry, because there are a lot of control and management bits used in this frame. Or for instance, a power bit, or for instance, other bits that are used in different procedures that could be implemented in the wireless LAN protocol. But now we will see the detail of the type and subtype IDs. There are a lot of different frames or frame types. Several are management frame types, typically, for instance, beacon, association request, association response, or in the case of control frames, we have request to send, clear to send, naturally data, and acknowledge. We'll see that. And even other different subtypes, for instance, when we could use the collision-free, the possibility to avoid the collisions using a particular methodology that we will see later, associated with those letters. Node collision, contention-free, contention-free. And the use of, for instance, the possibility to have a deterministic medium access control using a polling technique. But remember that there are different types of frames. Is not the case compared, for instance, is not the case of Ethernet, where all the Ethernet frames, in fact, are what we call theoretically the unnumbered information frames. Then we need to remember that when we transmit data frames, remember data frames, all those are data frames. When we transmit data frames, in fact, in the data field, remember here in the data or payload field of the frame, we transmit, in fact, an LLC frame. The LLC frame, LLC comes from logical link control, and it is specified by the 802.2 standard. The LLC could specify, for instance, with the first 2 octets, the destination and source service access point, the DSAP and SSAP. And for instance, when those 2 first octets are specified as an hexadecimal AA, then what we have here is what we call the organizational unique ID and the protocol ID. And the RFC 1042, in fact, specify that we could use this encapsulation, that is using those service access points, this control, that means unnumbered information frame with this code, this organizationally unique ID, and then these octet, in fact, octets are what we call the protocol ID. That is exactly the same that we use in the Ether type or frame type of Ethernet 2. Then, for instance, this permit to encapsulate within the LLC packet or LLC PDU, an IP packet, and so on. And within the IP packet, we could encapsulate TCP, UDP, and other higher level protocols. Another Well, remember then this particular possibility to encapsulate typically, for instance, the IP packets within the frames that are transmitted across wireless LAN network. The control frames facilitate the exchange of data frames between stations, and typically we have the acknowledgement, the ACK frame, the request to send frame, and the clear to send frame. We will see in detail those control frames in some algorithm supported by different mechanism of the protocols used. And finally, the management frames. There are typically different management frames, but some management frames are very interesting. For instance, the beacon, when we use an infrastructure mode, wireless mode network with access points, then the access point send periodically a beacon to announce its presence and provide the service set ID, that is an ID that identify the Wi-Fi zone and other parameters for a wireless station within the range of the access point. The association request, for instance, that could typically is sent by a station, and it enables the access point to allocate resources and synchronize. Then the frame carries information about the typically the wireless network the network connector, the interface connector circuit. I think that is circuit WINIC, including supported data rates and SACDs, that is service set IDs of the network the station wishes to associate with. If this association request is accepted, the access point reserves memory and establishes an association ID for the WINIC, for the station. The association response frame sent from an access point to a station containing the acceptance or rejection to an association request. If it is an acceptance, the frame will contain information such as an association ID and supported data rates. Typically, those are some examples of management frames.